having this maze game, we are actually going to learn. Got it. Yes. Okay. So we are going to learn the strategy how we can search in a real life system as well as in a computer system. So basically, these are two different things. How we can learn the search strategy, how we can build the search strategy in our human brain, what's the comparative analysis with the human brain, with the machines, and what's the difference between how the human brain will analyze the problem, all the search things, how we can search the things and how computer will search the things. So there is a huge difference, and this gap ultimately we just need to reduce. So this is the strategy how we can search the things, find the shortest minimum distance, or reduce the time complexity, reduce the space complexity. So all of these things we can learn by playing the game simply. So the next we will go through and directly with the search algorithms in artificial intelligence. Usually they are of two types. One is uninformed search, and another is informed search. So the difference is in between these two is uninformed search, where we don't have any kind of information in our hands. So we just we just have only one information, like I want to go there, nothing else in our hands. But we have to have some plans ready in our hands. We have to think about it, how we can reach there, how we can solve that puzzle. So this kind of information, this kind of search strategy we need to build in uninformed search. And what is informed search? So in this search strategy, we usually have a very good information beforehand. So we can use this information to build the strategy to reach the goal. And we will have some of the practical implementations in Python programming language, as well as I, I would like to have some of the small assignments for you, so to be engaged with. So that's why you don't feel bored or distracted anyway. So yes, so this is very important, I guess, so to make you awake. So yes, at the end we will wrap up the session by having some questions, queries, and some recap of search algorithms. So shall we start? Thank you. So, so this is the game. Can you please help me? So, so yes, here's the Prince Charming, and he wants to reach his palace, to his palace. So you can just look to this maze and think about it, something like find a way. You got it? What's your good name? Kyo. So can you please tell me what's the right path? This one? Shall we go here? Okay, no. Shall we go here? No? Okay. So shall we? Okay. Uh-huh. Continue. Here? No? Here? Okay. Here? Okay. Okay, so here, perfect. So yes, so you can see with human brain, you just got the results in few seconds, just in a second. But there is a difference between the artificial intelligence and if when we are working with computer systems. So now we are getting into the difference, how the algorithms, how the systems are going to work with this. Okay, so here's now we are implementing the search algorithms on this. It will see, okay, where's the state space? I will start from here. There is no other way. Okay, I will start from here. There is a 3 ways to go. Okay, where shall I start? Start state 1. Okay, and then it will go ahead in that direction and found, oops, there is no way. So it will just go back and come to start state 2. Okay, and then it will it will found like there is no way either, and then it will start state 3 and it will go ahead and found, okay, there is another puzzle here. Either I should go here, either I should go here, either left or right or up or down. So if we can just go ahead, it decided to go up because it is not so intelligent. Our brain is much intelligent in that way. So in our brain, neural networks are popping out constantly and very quickly. But in artificial intelligence and other computer system, it's not so quick. So this is the difference between the artificial intelligence and human brain. If we are comparing machine learning and artificial intelligence, what is the upper hand? Artificial intelligence, of course. Okay, so yes, it just go up and found another puzzle, up or down. So it is gone down and found, no, there is not any way. So he decided the else statement, the down one. Now it is having his way, again puzzle, this way or that way. So this way, it just went, there is no way. And here, just found. Goal state. So yes, how much time we spent in the artificial intelligence? 2 minutes. And with human brain, just a few seconds. So this is the difference between the human brain and artificial intelligence. And our main goal is how we can reduce this gap by train the artificial models so that it can quickly give us results, not like this, where we have to wait for 2 minutes. It's a huge time of our life. So the major goal of every artificial intelligence model, every neural network model, how we can reduce the time complexity, space complexity, so that we could remove if else statements in the code, and it will be intelligently, automatically can discover its right path. Right? So yes, and thank you so much. Now Prince Charming is at his home. So yes, starting with the search algorithms in artificial intelligence. So first is uninformed search. So uninformed search is basically where we do not have any kind of information in hands until or unless it's just having the problem definition. For example, if we want to go to Copenhagen, Denmark from Oslo. So I just want to give you the problem statement. Okay, you want to, I want to go to Copenhagen from Oslo. That's all I have. So you have, uh, yeah, a point. Is it visible to all? Am I visible? To zoom. So, okay, is here Oslo to B point, Copenhagen. This is the problem statement I have. There is not any directions are given, not any kind of other information in hands. So this is called uninformed search, where we do not have any kind of information in hands. What would be the mode of transportations, how I can go there, what should I do, and whatever else, nothing in hand. So this kind of search is also known as blind search, where we just blindly hitting some of the options and find the minimum cost. Mm-hmm. Mm-hmm. Okay. So yes. So also, can we relate this to maze game? Earlier we have discussed, where we just have the Prince Charming and the goal state, his palace, and we do not know anything else in between. We just had a maze, a very big maze, and we just needed to find the way. So this is kind of example for uninformed search algorithm. And the state is differ as is written only by the order and length of actions. So we can actually measure the complexity, time complexity and space complexity by the order, which order we are following. If we are following the start state 1, start state 3, and then start state 2, which was the right one. So the time complexity just increased, and also space complexity. But if we could intelligently trained the model, and it specifically for the first time it just chose the start state 2, the time complexity reduced, space complexity reduced. So yes, so that's why uninformed search is very much depends upon the order and length of actions. So each of these algorithms, we will have one graph, that is the start node and the goal node we will have. And we will then make the strategy that will describe the manner in which the graph will be traversed to the B point. So there must be some graph. I would say this is the B, and here is C, D, E, and it can be like this, and this. So we have to hope on to CDE, blue one. Thank you. So yes, so we have to hope on to these, all of these vertices or nodes, we can say, in a graph so that we can reach from point A to point B. Okay, so Okay. So yes, what is fringe? So this is the data structure where we just store all of the structures and possible states where we just hoping of. What's the whether we are using queue, whether we are using stack to follow that path and keep the vertices on. That is called fringe. So these are the data structures terms you just need to learn. Yes, as compared to real life examples. Hmm. So tree that resolves while traversing to the goal node. So for example, this is the graph, and if we are traversing here, for example, A, and then I would like to go to C, and similarly, it can go to D as well, then it will go to D as well, and C will go to E, and B will go to B, and E also go to B. So this kind of structure is called tree. This is graph, where we do not have any information. We have to traverse the graph. And then this is the traversed graph called tree. Okay, so yes, a solution plan, which is a sequence of nodes, which is a sequence. Solution plan would be like, for example, if we want to go from A to B, what would be the solution plan? It will be according to search algorithms, different search algorithms. It is just an example. Okay, so here we can see A, C, E, B. This can be one solution, and other solution can be A. What can be other solution? Mm-hmm. Thank you. So yes, there are two possible ways to reach A to B. So this is called solution plan. Problem graph, strategy, how we can traverse towards A from B, and fringe, whatever we are using, whether we are using stack, whether we are using queue. I assume everyone is very well known by the terms stack and queue. Mm-hmm. Okay, perfect. So yes, and tree, whenever we are traversing the graph. So that would be a tree, and solution plan would be, what would be the plan, possible plans. Okay, so these are, we will use these terms forwardly for the search algorithms. Starting with the different types of uninformed search algorithms. So first is depth first search, and breadth first search, and uniform cost search. So yes, start with the depth first search. So usually we are using stack data structures for implementing depth first search. So what is it in the depth first search is the standard each vertices. So this is called the points A, B. This can be called node as well, and vertices as well. Yes, vertex, one vertex, and multiple vertices is vertices. So yes, for the graph. So for this, we divided the solution plan in two different stacks. The first one is, for example, visited, And second one is stack or not visited. Okay, the purpose of the algorithm is to mark each vertex as visited while avoiding cycles. So no one wants to go in the loop whenever, if you are just for example, if you are having a tour within a Oslo as well, if you want to go to that island and come back and want to have some of the tourist places within Oslo, and you don't want to hop in and hop out, hop in, hop out on the same place. Like you want to usually want to go around so that you do not want to repeat the tour or anyway. So yes, in same in the search algorithm where we avoid making the cycles any loops. So first algorithm is we will start by putting any one of the graph's vertices on top of the stack. We can start with any of the vertex here. For example, I just have one example to show. Yeah. Um, can I have that duster? Okay. Hmm. Okay, this one would be better. Hmm. I have some examples, other examples as well for you people. Hmm. For example, we have this graph A, B, C, D, and E and F. So yes, this is the graph. And we just start by putting any of the, for example, here is two different stacks. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So this is visited, and this is called stack. So what's the normal principle of stack? Anyone wants to volunteer? Uh-huh. Anyone in the classroom? Whether it's a first in, first out, whether it's a last in, first out, whether it's a first in, last out. You are correct. Last in, first out. So stack is LIFO, last in, first out. Okay. So yes, whenever we are stacking, for example, the plates, last in, first out. Okay. So yes, so this strategy, this principle will work out. We will use this principle in this depth first search. So for example, here we can start our algorithm from any of the vertex. For example, A. So A is visited. Okay. And what else? In the stack, it's children. B and C. Okay. Hmm. And then what is it? Take the top item of the stack and add to the visited list. What is the top one? B. So in next one, what would be in visited list? B. Yes. And what would be in the top of the stack? Who is the child of the B? Because this is the depth first search and we have to traverse, like, first we selected A, who are the child of A, B and C. Now we just get B and C in the stack. Who is the top of the stack? B. And who is the child of B? D. So it will be D and C as it is, like a plates. Mhm. So yes. Next, what would be in visited list? What is at the top of the stack? What is at the top of the stack? D. So A, B, D. Now the plate C is on the top of the stack. We have two children. Who are the children of C? E and F. Mm-hmm. So yes, it's visited and on the stack. So what would be the next visited one? Hmm. A, B, D. Next one, C. Next. So it will be like E, F. So what would be the next? Hmm. And next? Hmm. Okay. A, B, D, C, E, F. This is empty. Stack is empty. All plates are here. So this is the way for depth first search, where we are traversing the tree or graph in the depth wise. First, we select any of the vertex, and then we see who are the child, adjacent child of A selected vertex, and then we will go for what is the top of the stack and then watch, is there any child of that what we have visited? Yes, we do find one child of what we have visited. And then we just visited D. We just see, is there any child available of D? So no, we come up with the next plate. C here. Okay, so then we just need to see, is there any child of visited vertex? Fine. So yes, we found it, E and F, and then E and F on the top of the stack. And then we just selected E. Is there any child? No, it will be visited straightforwardly. And then the top of the stack, it's F. Is there any child? No, visited. We are completed. Mhm. So this is the way for depth first search. Yes. So another example is this. You just need to get some hands on solving the problem now. So I can just give you the tree-like structure for this. 0, 1, 2, mm-hmm. So it's yeah, this is graph. So you can traverse it like that only. Mm-hmm. So I will show you. So yes, if we just yes, the child of 2 is 4. This is the graph, exactly same. Okay, so now we are going to solve this. How we can solve it? If we just start with 0 on the visited list, 1, 2, 3. That's on stack. That's on. Oh, thank you. So now you will tell me what would be the steps. I'm sure you will. Okay. Hmm. 1, 2, 3. Okay. So who are the children of 0? The visited one. 1, 2, and 3. Nice. And then who is the top of the stack? 1. Where should I write 1? Here. Mm-hmm. And then what is at the top of the stack? 2. And then is there any child of 2? Mm-hmm. 4. And then 3. That's all? Okay. So yes. Who will be visited now? 2. 4, 3. And now 0, 1, 2. Next 4. Yeah, stack B. And what would left in stack? 3. And next would be 0, 1, 2, 4, and 3. So in that way, we have visited all our vertices. So what's the output of this? 0, 1, 2, 4, 3. In that way, because this is the graph. This is the drawback of depth first search. We are not getting any directions. We are not getting any kind of information in hands, how we can traverse the whole tree or graph. So if we just go through, see all the information what we have implemented here, it's there. The same output is coming on. Am I correct? So yes, in that way, you can easily go through depth first search. Good. So you have already learned one search algorithm. Congratulations. So yes, another assignment now. I want you to solve this tree or graph. If you want any paper or pen, I can provide. Shall I? Okay, I should 5, 3. This is the answer from CC. Yeah. Anyone who has solved this graph online as well, they can raise their hands or write the answer in a chat section. 5. 5. Mm-hmm. Mm-hmm. You're done? Okay. Okay. Shall we go through the solution now? Are you ready? Okay. Mm-hmm. So, yes, this is the answer. So, yes, 5, 3, 2, 4, 8, 7. Clap for yourself. Yeah, perfect. So, you are Congratulations, you're done with one algorithm. It's depth first search. So now, if you want to get some hands on Python programming, we can go for that. Do you have any PyCharm or any IDE, Python IDE with you at the moment? Or Jupyter Notebook or anything? Mm-hmm. So yes, this is the code where we can implement and see the implementation of the depth first search, where we have exactly same graph in the code. And we first initialize the graph where we have used the list and dictionary as the dict in Python programming language. We just made one function, it's set, and yes, is another function, DFS, it's depth first search, where we have the visited stack and graph, and what would be the node, the starting node. Okay, and if node not in visited, then print node in a visited one. Visited dot add node, and then for neighbor in graph node, the next in the list DFS, then again it will just continue the loop. So this is the code for having the depth first search, and then it will just start from 5, vertex 5. And then if we want to start with 3 or 7 or 2 or 4, so it will just make the changes in results accordingly. So you can try if you want to, and make some changes with the starting node here and see what would be the change. This one. Mm-hmm. So this code, this is the just print command, just to print this line, this statement. And this is for calling the function, where we have called the visited stack and the graph here. It will load the graph. It will just make the list or the list of the stack. And here, what we are want to start from here, node. Yeah. And you can make the changes with this and see what would be the change. And ask me if anything. Very good. We will have 2 more minutes, and then we will then be forward to next algorithm. Mm-hmm. Mm-hmm. Yeah, as Isa said, anyone can mute yourself and ask the question or anything. If you find any difficulty in running this code, you can raise your hand or unmute yourself directly and ask. Shall we go forward? Mm-hmm. Mm-hmm. Very nice. Mm-hmm. Yeah. Hmm. So yes, thank you, sis. So yes, in that way you can just implement this DFS, depth first search, in the programming language. This is very much straightforward and very easy. So moving towards the next, sorry, this is the complexity of depth first search, where we are representing the complexity. As I said, there is time complexity as well and the space complexity. And time complexity would be depends upon the order where we are traversing and the length of actions, what we have discussed previously. So this represents the number of nodes. What are the number of nodes? Four, and the number of edges. For example, here edges 1, 2, 3, 4, 5. So this is called edges, and these are called nodes or vertex. So time complexity is the combination of number of nodes and number of edges. So yes, and the space complexity is the number of nodes only. But what's the space acquiring? How much is the complex graph is? So that is the space complexity. How many nodes the graph has. So this is the space complexity, and time complexity is a combination of number of nodes and number of edges. And what are the applications of DFS algorithm? To find the path where, for example, our maze game. And another example is if we want to go from Oslo to Copenhagen. So there would be different modes of transportation, for example, by bus, by car, by ferry, by airplane. So each of the, what would be the shortest minimum path you would prefer. So in that way, you can also, if you want to make a project in Python, to find the minimum destination, or like a Google Maps, it will just show you the shortest minimum path. Okay, so yes, if you want to make such kind of applications, mobile applications or any kind of web application, you can make the use of depth first search, but it is just make sure it has a huge time complexity and space complexity. So our major goal is to reduce these both complexities. Okay, and yes, the another application is for detecting cycles in graph. Is there any cycle? Is there any loop in graph? Like this is the loop going on. So for detecting any cycles, any loops in graph. So yes, moving forward to the breadth first search. So this is kind of very similar to depth first search, but some of the obviously there are some difference in breadth first search. In depth first search, we are traversing from top to bottom. Here we are traversing from left to right. Okay, so yes, for this breadth first search algorithm, we are using what data structure? It's queue. So what's the principle of queue? Very good. So we follow first in, first out in queue data structure. So this thing has to be remembered. Like for depth first search, we are using stack because we are going from top to bottom, and for breadth first search, we are following the principle of queue because we are traversing left to right. Okay, so the same uh, thing, if we just apply breadth first search here or the earlier one, yeah, maybe later, start from the easier one. Hmm. So, yeah, this one, A, B, C, D, E, F. Here we have visited queue, and here we have the empty queue. Now we start from A. Who would be the children of A, B, and C? Mm-hmm. So what's it? Start by putting any of the undirected graphs vertices at the back of Q, first in, first out. So here is the front of Q. So the first point is the front of the queue, and then take the front item of the queue and add it to the visited list. So we already have visited A, and okay, so we can go from here. Like front, this is the first step. Okay, we selected A vertex and put it in queue, and then it is on front and take it to the visited list. So the next would be A, and who are the children? B and C. So who is at the front? B. So we can visit B now. A, B. Mm-hmm. So who left in the Q, C. And is there any, yeah, create the list of that vertex adjacent nodes, add the ones which aren't in the visited list to the back of the queue. So we just need to, so C, what would be the next child, next children of this? Mm-hmm. Both, because B has already been visited. So we have to check whether this one or this one. So in that way, we start from the left side each time. So we come up with D. Hmm. No, only D. Hmm. Because B has already been visited. And then we see what left on the left side. It's D. Okay. And then E and F as well, because we have to traverse from left to right, left to right, left to right, this way. D, E, F. And then what we have to do, A, B, what would be at front? C, D, E, F. And it will just key forward and move to visited list one by one. So the ultimate solution plan would be A, B, C, D, E, F. So this is the breadth first search. For example, start by putting any one of the undirected graphs vertices at the back of the queue. Take the front item of the queue, and add it to the visited list. Create a list of that vertex adjacent nodes. We just need to have it the adjacent nodes B, and then C. Adjacent nodes, we don't have any. Hmm. Mm-hmm. Yeah, it will just see, is there any adjacent? So no adjacent, so we just move forward here. In depth first search, but we are traversing about the child. But here we are traversing about the adjacent nodes. This is the difference in depth first search and breadth first search. And add the ones which aren't in the visited list to the back of the queue. Simple. Any queries? Mm-hmm. Any queries over the Zoom? Fine. So yes, we keep repeating the steps 2 and 3, where we are traversing towards left to right, and keep finding is there any adjacent node or not. And in that way, we are having this solution plan, right? So yes, we come up with again this one. So we can go through this as well. So this is 0, 1, 2, 3, and this one, yeah, 4. Perfect. So yes, what would be the output of this? Mm-hmm. Mm-hmm. 0, 1, 2, 3, 4. Yes. So how? First, we visited 0, and who are the adjacent? Next level, 1, 2, 3. That would be in queue. Then at the front, it will be visited. Okay. Then what next? 2, 3. It will come forward in the queue and 3 as well. And then it will check, is there any adjacent to 2 visited? But there is 3 adjacent node at the same level. Here, it will visit it again. So it will see, is there any adjacent node to this? No, it will go down and add it 4 in a queue. And then in next step, it will just come up with 3 as visited, 4 at the front, and then 4 in the visited. So in that way, you are having breadth first search. Simple. So yes, again, we come up with another assignment. So you can have any solution. Mm-hmm. 537248. Everyone, shall we see? Yes, 537248. Congratulations then. So one more search algorithm you have learned successfully. So this is kind of straightforward breadth first search and depth first search. Mhm. Very good, very intelligent audience I have. So yes, this is the another um, Python code for this. I have implemented. You can take a picture, or maybe you can have some practice later on. Or you can just keep the same graph and visited. Here's the two different lists and visited in queue. Here's the definition of breadth first search, where we similarly calling by the visited list graph and the first node, and the visited append that node to be visited in, and in queue as well we have to append the adjacent nodes in a queue. So while queue creating loop to visit each node. Mhm. And yes, in this we have to pop out the node which is on the front of the queue. Okay, so in that way, this is the breadth first search, and we start with the 5, and you can start with any of the vertex you want. Okay, great. I can show you the output of this. Hmm. Breadth first search. See this one, 537248. And for depth first search, it's 532487. So this is the example you can run later on. Yeah. So in that way, you are done with second algorithm of uninformed search in artificial intelligence. So the time complexity and the space complexity is similar to depth first search in this. And what are the applications of depth first search is to build index by a search index, and for GPS navigation as well we can use the breadth first search, and for the pathfinding algorithm. So applications for depth first search and breadth first search is more or less similar. So you can go for any of the algorithm if you want to have such kind of projects later on. So yes, the another is uniform cost search. Yes, so this is actually very much different from breadth first search and depth first search. So the major addition in this algorithm is how we can um, sum up, or additional information is like we have the cumulative sum of cost. So each of the edge here, for example, here we have some weights for, for example, and 12, 3, 4. So these weights or these costs make it more affirmative which path we have to follow to reach from A to F, for example. So for breadth first search and depth first search, it is kind of undirected, blind search. But in uniform course search, we do have some meaningful information in hands, but it is not that much meaningful, but it is quite meaningful to find the path, to find the shortest distance, to find the minimum distance from point A to B. Okay, in depth first search and breadth first search, we are traversing the whole tree or graph, but here we are finding the exactly what shortest minimum path we should follow to from A to point B. Okay, so for this, the cost of node is defined as is the cost of that node, particular node, is cumulative cost of all nodes from the root. So for example, if we want to find the cost of F, what would be the cost of F? If we start from A, if we start from A, what would be the cost of F? It's cumulative sum of these two. 4 plus 4, 8. So this is how we can um, calculate the cost, cumulative cost of each of the nodes, and found if we want to go from, for example, this way, what would be the cost of F? There's two different ways. So if we calculate, it's 1, 1, 13, and 14. This way, if we follow A, B, D, and F, it will cost us 13 and 14. And if we follow the straightforward this one, A, C, and F, it will cost us 8. So this would be the solution plan. Okay, so yes, the uniform cost algorithm is like we use the priority queue here. Who would be the priority? For example, here it's 4. We just see, we start from the A and we just need to decide which way we need to go. Here the cost is 4. Here the cost is 1. Who will be the prioritized? 1? Yes. Very good. So 1 would be prioritized. Minimum distance, high priority. So we just go from this way. And now we just see, for example, is the 1, which what's the next followed path would be? B to E. Hmm. B2E. First, we have followed this. First, then we have followed this. And then there is not any connection here. What should we do? C, 3, and then C2, F. So what would be the cost now? 1, 2, 3, 4, 5, 5 and 4, 9. Okay. So if we just follow one, A, B, E, C, F, 9. Still, we have the better one. So in that way, we have to keep calculating the minimum cost by traversing all of the nodes here. This is the drawback of uniform cost search. Okay, so we have to find each and every of the possible track and find the minimum one. So this is the solution for the uniform cost search, but there is a drawback. We have to make different combinations. We have to find all of the possible combinations. Hmm. So yes, this is the uniform cost search, and now we are going through one paper and pen and paper example. So yes, in this graph, as you can see, there is a roadmap of a country in which there are some cities. These are the cities. Imagine. Okay, so and a couple of edges connecting these cities. These are the edges who are connecting these cities. So target is to go from city node S to G. We have to go from S to G by following the path with the smallest cost, shortest path, minimum distance. Okay, so yes. Okay, so what would be the path you will follow? So you will go either this or this. What would be the higher priority? A, and then B, straightforward. And what would you now select? Is the both equal? Hmm. Both equal. So algorithm, we are intelligent, but algorithms are not intelligent so much. So, so yes, definitely uniform core search is not so intelligent as our brain. So yes, it will go either this or this. It will calculate both ways. Okay, so it will go this if what would be the cost? 3, 4, 5, 6 if we follow this path. And if we will follow this path, the cost would be 5. And if we will follow this path, the cost would be 6. 6, 6, 5. So the solution plan would be this. Mhm. S, A, B, and G. So in that way, your uniform search algorithm is worked. Any question? Any queries? Mm-hmm. People on Zoom, it's all clear or all clear? Okay, perfect. So yes, here's the task for you. So you can you can try. Maybe I can make that graph, the bigger one, here for your understanding. So B, A, D, C, S, G. 1, 3, 3 C 1. So you have the problem to reach from S to D. Problem definition is you have to reach from S to node G. What would be the possible paths and what would be the cost and what would be the correct solution plan with the minimum cost? You can have a look. Okay, 3. 1, 1. Okay. Uh-huh. 3. Now fine? Yeah. Thank you. So yes. We have to start from S and need to reach to G. Mm-hmm. You just need to see the directions. If you are going from S to A to C, C to D, and it will go down. No. Mhm. So it will go back only in one. Very good question. Go back in only in one situation where we have cost 0. Only then it will come into the loop situation where we don't have any cost, but we do have cost here. So if you have visited one, then it's fine. Mhm. Anyone with results? A C S A C D G. And what would be the cost? Hmm. Mm-hmm. Hmm. Mm-hmm. Yeah, yeah. So you just need to go. So this is the one path you have made. So SACDG. So this is the one path, and it's done. Then you have the again the whole graph with you. Yes, SACG. And what would be the cost? For hmm. Hmm. Yeah, perfect. So yes, so there are some possible tasks or ways to go is S to G directly. Its cost is 12, and you come up with the different way S A C D G, what cost us 6, and another way is S A C G, so it cost us 4. So any other, how much is the cost? 10. Okay. So what would you prefer? So what would be the solution plan? SACG. Yes, 4. So that is the solution for the uniform cost search. Mm-hmm. Yeah, but this is the best possible way. Hmm. Hmm. Yeah. Hmm. Hmm. So it will start from the prioritized one, but it it's in nature, like it will find the other ways as well who are left. Okay, so prioritized will be, it's a prioritized, not avoiding any other paths. So we are prioritizing the minimum shortest distance ones, and then it will automatically traversing the other possible ways as well, which we left earlier in the prioritizing task. Mm-hmm. Yes, question. Yes, but we have to focus on the prioritizing thing first because we are using the priority queue in this algorithm. So this is the thing we have to follow. This is the drawback of this algorithm. So yes, yes. Mm-hmm. Here, any other query over the Zoom? Okay. So yes. Mm, So yes, see, here are some of the possible solutions. 6 with 12 and 10 and 4. So we have selected the fourth one. So as we have already discussed, these algorithms are not so intelligent. So it will prioritize, it will work according to it is written, like a prioritizing the things, but it will definitely find the other ways as well. Hmm. So yeah, so the time complexity needed to run uniform cost search is big O notation with the branching factor. What would be the branching factor in that case where we are starting? And then 1 plus optimal cost. What would be the cost of that edge? And epsilon is cost of each step, cumulative. So in that way, we are having the time complexity of this. And what would be the advantages? UCS is complete only if states are finite and there should not be loop with zero weight. So state should be finite. It should not be infinite states. Uh, and also UCS is optimal only if there is no negative cost. So in real life as well, this is not the real case scenario where we have the negative or negative cost or negative kind of weight to go to move from here to here. So this is unnatural thing. So if but in machine in error anything can happen. We can have the negative negative cost from moving from A to B. So this can happen. So if such kind of errors, such kind of miscellaneous things are present in our graph, so it can diverge the algorithm in a wrong direction. So this can be disadvantage, but there should not be any negative cost and the zero weight to have the advantage of this UCS over the depth first search and breadth first search. The disadvantages explores options in every direction. See, it will prioritize first with the minimum cost, but it will explores the option in every direction. So this is the disadvantage of this. So no information on goal location. Still, we don't have any information in hands, any directed way, so that we can just focus on the minimum only, not any other direction. So yes, very good point. Very good discussion. So yes. So now is the time for 15 minutes break. Much needed, I would say. So have a coffee, have a chit chat, or have some break to your brain. Thank you. And we will be back on exactly 11 would be fine. Mm-hmm. Thank you. Mm-hmm. Hmm. Perfect. So, yeah, welcome back. Yes. So we start with the informed search. So that was the uninformed search we have covered in the first half of this tutorial. And now we are going to cover informed search. So what's the difference? Anyone can tell me what was the difference between the uninformed and the informed one? Hmm. Mm-hmm. And informed search. Now we have the information about the goal state, which helps in more efficient searching. For example, this information is obtained by something called heuristic. Heuristic meaning like so yes. So what does it mean? Heuristic. So it enable us or enable the algorithms by themselves to learn by their actions on the consequently basis. So yes, this is the meaning of heuristic. So in informed search, basically we are using the heuristic approach as a function to reach from the source to our destination. Okay, so it that estimates how close the state is to the goal state. For example, if we are using clustering algorithms, have you known of the clustering algorithms in machine learning, where we are using um, for KNN, K-means algorithms, and we just calculate Manhattan distance or Euclidean distance, where we just need to make the clusters. Okay, here's the one point, and here's the other point, and we calculate the distance from the goal, from the source to the goal, and calculate what would be the minimum distance, and make that cluster separate, and that cluster separate, that cluster separate. So this kind of information we have in informed search. So this is a very good example we already have and implemented and learned in machine learning. So they already have implemented this informed search algorithms in such kind of methods in machine learning. So yes, different heuristics are used in different informed algorithms. So basically, we have two different types of informed search algorithms in artificial intelligence. It's a greedy search and A star search. So these are basically two types of informed search. So first, we come up with greedy search. So we expand the node closest to the goal node. The closeness is estimated by the heuristic hx function. So we start with the one node, and then we just try to expand that node towards the goal state or goal node to reach that, and then estimate the closeness. What would be the closeness, like we did in the UCS, uniform cost search. In that algorithm, we have calculated the cumulative sum of each of the nodes, but in greedy search, we are not calculating the cumulative sum of each of nodes to reach from source to destination, but we do have the heuristic hx function for each of the node. Mhm. So yes, for heuristic, a heuristic h is defined as hx, which estimates the distance of node x from the goal node, like Euclidean distance, Manhattan distance, or any other distance. And lower the value of hx, closer is the node from the goal, like we do in any of the clustering algorithm. Mhm. So what would be the strategy for the greedy search algorithm? Expand the node closest to the goal node. Is that expand the node with a lower h value. In UCS, we have to find the lower cost, the minimum cost. Here, the minimum lower h value. So we start with the example, pen and paper example here. So this is the graph we have, and the problem statement is we have to reach from S to G. So what would be here? Inside that node, we have the heuristic value instead of the cost of edges, like we had in uniform cost search. Okay, so for this, we are using the priority queue as we used in uniform cost search. And yes, now we have to decide. Here, the cost is 7, where we have to move the minimum heuristic cost, D. Okay, so you can see in that tree structure as well. So we come up with this, and then we have to decide whether we should follow E or B, which is the minimum heuristic value, E. So we just move from S, D, E, and then G. So this is the path. Very straightforward, less complex. Then UCS. Mm-hmm. So what would be the heuristic value? 7, 15, 5, 7, 5, 3, 15. Okay, so that is the path, and we are done with greedy search. So this is the advantage of using if we have some informative information in hands instead of undirected graph like we discussed in uninformed search algorithms. So what's the advantage of this? It's works well with informed search problems with fewer steps to reach a goal. And what can be a disadvantage? It can turn into unguided DFS in the worst case. As you can see in the tree structure, it is just similar to DFS, where we are constantly going down and looking for the children of each. So this can be turned into DFS if it is not much guided with the directions here. So this is the main advantage. We have the directions, but if we are having not any directions, it can turn into DFS. Mm-hmm. Mm-hmm. If we have the same value for everything, yes, it can turn into DFS. Hmm. Any other query? The candidates online. Mm-hmm. So it's time to get some brain exercise again. So yes, here is a graph. Very straightforward, very simple, isn't it? So, so yes, find the shortest path from node S to node T. You have to find the shortest minimum path from S to T. What would be the solution? Shall we discuss? Mhm. So yeah, so this can be a solution. We start with the S5, and what are the directed to adjacent to S? It's both directions with the heuristic value 4 and 4. So B and D. We just see there is what is the, we can actually go from B to C, because here we have to traverse B first, because we have B first vertices and we have to follow this path first. If we are traversing B here first and B later, and then we have to traverse D. So there are two different ways to reach T here, but this is the one solution. And the other solution could be if we can traverse D first. Okay, so yes, so first we traverse B because they have same heuristic values, and D. And then we just go from B to E. And who are the adjacent to E? These both, D and F. Who will be prioritized? Who will be prioritized? F. So we will cross D. That path will be neglected. And then we just move forward to F. And then F, what would be the adjacent one? G. And then G, we have two adjacent nodes to G. What would be the prioritized one? Minimum heuristic value, I. And then we neglected C then. Okay, we come up with I, and then L, and then T. So this would be the shortest path. In that way, this greedy search algorithm works to find the shortest minimum path from S to T. It no, no. Hmm. It will be same if we just go from this, but it will just follow the simple path like this one first, and this. It will just, if we just select this one first, it will see, okay, this is the adjacent E. Then again, it will traverse this or this. It will go down if we just follow this path. Then what would be the heuristic value? 5 for 9, 9, 12, 14, 15. Same heuristic value, but if we want to approach to this first and this later. So that could be also solution, but if it finds 15 here, sufficient. That's all. So this is the advantage of greedy search algorithm. Any queries? All clear? Mm-hmm. Perfect. So any queries over there on Zoom? So the Python implementation can be found on this link. You can have a picture, so you can find a very good example for explaining. I can, if uh, 1 second, I can go through and show you. Hmm. So this is the exact example you can see, and point by point and step by step it is explained in this. So my slides would be shared to you, everyone, after this session. So everything is explained step by step, how in this they have calculated Manhattan distance is the pseudocode. Okay, so how to calculate the heuristic value, and yes, here's the code for that, and pen paper example. So they have used the grid values so that how we can move around the graph. Hmm. So you do not need to go into that much explanation. You just need to have the understanding of how the algorithm is working. Okay, so yes, everything is explained this way, or you can have the solution to have the second one as well. Then, hmm. So you have the code here. You can try with your Python scripts. Yeah, perfect. And you can just select Euclidean distance as well and see whether is a different any different results or not, or any cosine similarity or any other distance you can use. Here they have used Manhattan distance, but you can try any other method as well. Here they have built the graph algorithm where they just inputted the graph, what's the start and what's the goal. And you can just try to change the start and the goal node as well and see the difference to make more better clarity of the code and algorithm. So this is the greedy search algorithm we have. Hmm. Hmm. So the next is A star search. So what is the A star search? So it's a combination of the advantages of uniform cost search as well as the greedy search. Still, the greedy search has some limitations, but it will overcome the limitations of for both uniform cost search and greedy search. Here as well, we use a heuristic function, as well as in addition to that, we will use the cost as well, cost of the edges. So that combination of cost of the edges and the heuristic value at each node to compute what would be the actual cost to reach from the source to destination. So yes, the heuristic is the summation of the cost in UCS. It was the cumulative cost of the edges from A to B, denoted by GX. We denote this UCS cost as function of GX. And the cost in the greedy search denoted by HX is the heuristic function. The summed cost is denoted by FX. So here in a search algorithm, we sum up the cost of GX and HX and denote as FX. Okay, so heuristic A star search here, HX is called the forward cost. Obviously, it has heuristic cost is of each of the node, so it will be a forward cost and is an estimate of the distance of the current node from the goal node. And GX is called the backward cost and is the cumulative cost of a node from the root node to the destination one. It will just have the cumulative sum of each of the previous edges from the source to destination, but the heuristic function is of the forward cost. What would be the distance from this node to the goal node? And then accordingly, it will just come up with the actionable thing for the next one. Mhm. So yes, A star search is optimal only when for all nodes, the forward cost for a node HX underestimates the actual cost A star X to reach the goal. This property of A star heuristic is called admissibility. So it should be greater than zero. Heuristic cost obviously should be greater than zero and less than what would be our calculated sum of cost. Okay, so what would be the strategy? Choose the node with the lowest fx value. Obviously, we have to choose the lowest one only for all the algorithms. Okay, so this is a strategy for A star, and this is the graph for implementing the A star search. So, yes. So in this, we have to move from S to G. Here you can see we have the cost of edges as well as the heuristic cost per each node. So we have to sum up with, we have to focus on both of these costs and calculate the fx in the A star search. So first of all, we just come up with SH7. What would be the prioritized one? 2 or 3? Hmm. 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 So it will see the both directions and prioritize the minimum one. Hmm. Hmm. So S, sorry, HX is 7 plus 2. Sorry, this one 9 and 3. This one. So here is 12. Okay, if we just select this path, 9 and 3, here 5 and 2, what would be the sum? 7. So we will follow this path, D. So now we will see D has two path. One is E, which is 4 and 3, and here 4 and 1. What would preferable? B, SDB. See? Okay, and then now we see B has two different paths, B to C or B to E. What would be the, it's 4 and here it's 4. So either of directions can be made. Here we can see both directions are equivalent. So it's our situation or our decision which way we have to move forward. Okay, so if we just see in a both directions, if we go from C to G, what be the 4 coast? And here, if we just go from E to G, it's 3 only. So what would be the solution plan? It's E with 3. So more, much clearer, very good information we have. Instead of there is no information in hand, we have the directed graph. In each and every situation, each and every node, we have very meaningful information so that we can decide straightforwardly, unless we are traversing again and again for the whole graph. So we saved our time, but there is a space complexity still. Okay, so if we are making a very good intelligent algorithms, we have to balance the time complexity as well as the space complexity. If we are, there is always a trade-off between the time complexity as well as the space complexity. If we are reducing the time, it will take space. If we are reducing the space, it will take time. So, so yes. So this is the thing with A star search algorithm, more efficient, very straightforward. Clear? Any query? So yes, so what would be the final cost is 4 plus 3 is 77. So it will just directed the last one, 4 plus 3, it's 7. Perfect. So the cost is 7. And we will follow this path S, D, B, E, G. That's good. So yeah, so we are actually done, and congratulations for all of the algorithms we used in artificial intelligence. So these are the 5 major algorithms we usually use to build methods or any kind of clustering algorithms or any of the neural networks or in machine learning as well. The basic behind all of those methods in machine learning and artificial intelligence is these searching algorithms. Depth first search, breadth first search, uniform cost search, and then informed search algorithm, it's greedy search and A-star search. So yes, so it's again the wrap up exercise time. Let's get started. So yeah, I just want to recap some of, if you can solve it for me, what would be the depth first search output for this? Everyone agree with Sisi? And yes, we have A, B, D, C, E, F. And what would be the breadth first search? Yeah. A, B, C, D, E, F. How? How? Okay, perfect. Thank you. So yes, so now I'm pretty sure everyone is very much gone through the basic search algorithms is breadth first search, depth first search, uniform cost search, and greedy search and A-star search. Do you have any query or? Hmm. Hmm. So it will be given to you beforehand. Mm-hmm. Mm-hmm. Okay.
You want to try something fancy? Go below it. Speak to this. Yeah, the red one.
Yeah.
All right.
So yes.
All right.
Ask it again.
Yes, I was wondering in the greedy search and A-star search, like if we have to, for instance, do the route planning stuff, how is the value inside of the nodes given? Like, how do you, when you construct the graph, how can you?
So we do not need to construct the graph with the heuristic value. So this is the advantage of informed search algorithm, that you have the information in hand beforehand. So you will have these heuristic values beforehand, and you just need to decide what way you have to follow.
Yeah, but like let's say these are cities. So someone has to put the values, like to give you these values, even if before the algorithm. So how are they found, like these values before the algorithm, I mean? You know?
So this is because of the, you must have some ground truth available. Maybe historical data you would have. For example, you want to go from Oslo to Copenhagen, and you have the different modes of transportation, by bus, by ferry, and someone come to you and say, okay, bus would take this much time, and ferry would take this much time, and you have to just make the decision based on those particular values. Maybe he will come up with the information like, okay, bus will take 37 hours, or ferry will take 19 hours. So what would you select?
Okay.
Ferry. So this is the advantage of informed search algorithm. You have the information in your hands as compared to uninformed search.
Okay, great.
So you don't need to come up with your own information like we did in undirected, uninformed search, but you have the information available and you just need to make the decision.
Okay, great.
Any other question? So I would say thank you so much for the wonderful participation. So it was being a very nice session, and yeah, I enjoyed a lot, and hopefully you too. And I hope it was a productive session for all the participants. Yes, thank you.
So everyone, let's give Rashmi a applause. We can also do virtual, I think. I don't know.
Thank you.
Thank you very much for you and to Morten for preparing this presentation. I think we are able to share the slides with the participants.
Yes, definitely.
So that you can also try out the links and the code excerpts that she shared with us. And if you would like to follow the following NAIS sessions and the tutorials, please contact me. And we're thanking again Rashmi and Morten.
Thank you.
This is the end of our tutorial. Thank you for participating.
Thanks.